The Daily Code Snippet. This past week, we reviewed units of measurement for web. It is important to understand units of measurement for the web. With print design, we have points and picas. With print typography, the point is the smallest unit of measure. The actual size of a point has varied over the course of many centuries and has been interpreted differently by different countries. The pica is a basic unit of measure for American typography and represents 1/6 of an inch. Pierre Fournier, a French mid-18th century punch cutter, type founder, and typographic theoretician, was one of the people who defined a point system. His idea was to generate different type sizes by multiplying a single minimum unit derived from the division of the French royal inch, pouce. The pouce was divided by 12 to calculate one ligne, which was then divided by 6 to get 1 point. When Benjamin Franklin served as ambassador to France, he spent time with the Fournier family and wanted his grandson, Benjamin Franklin Bache, trained in printing and typography. So he arranged for him to study under Francois Didot. Didot had created a competing point system to that of Fournier. He kept the subdivisions but based the system against the royal foot, so that Didot point is exactly 1/72nd of the pouce. This meant 12 Fournier points equals 11 Didot points. Bache eventually set up a type foundry in America and brought with him samples of Fournier type, and it was later proposed by Nelson Hawks that the American inch be divided by 6 to create the pica, and that 1 pica would equal 12 points. This became the American point system. The world continued to have conflicting systems, however, the British came to accept the American point system in 1898. After much debate, for desktop publishing, 1 pica equals 1/6 of the British American inch, and that equals 4.233 millimeters. 1 point equals 1/12 of a pica, which equals 1/72 of an inch, which equals 0.3527 millimeters. So how does this translate to web typography? A pixel is the smallest unit of digital image data without actual physical size. Pixels are used to display an image on screen or print it. Screens have their pixel density measured in ppi or pixels per inch, while printed images are measured by dpi or dots per inch. This means that the same amount of image pixels may result in hugely variable physical sizes. Ergo, a 100 by 100 pixel image may be huge displayed on an outdoor advertising screen, or tiny when printed on paper at 300 dpi. The earliest Macintosh screen had a display with a resolution of 72 ppi, which would mean that 1 point would equal 1 pixel. However, screens that followed had a resolution closer to 96 ppi. At this resolution, 1 pixel equals 1/96th of an inch, 1 pixel equals 0.75 points, or 12 points would equal 16 pixels. 16 pixel type is a standard text size for most browsers. An M is a unit equal to the current point size of a typeface. So if our typeface is 16 points, then 1 M is 16 points. So no matter what typeface we are using, 1 M is 16 points. An M dash would be 1 M wide. It is called an M because it referenced a capital M in the typeface whose size was typically the same as the point size. When using metal type, the point size was equal to the height of the metal body from which the letter rises. A given letter could not exceed the M. The letter M was generally cast the full width of the square blocks or M quads. Here is an illustration of metal type so you can visualize an M. However, when type went digital, an M became arbitrary as a given typeface designer can determine settings. However, a typical digital font will have a cap height of 70% of an M and an X height of 48% of the M. This is a reminder of the typographic terms described. If we take a font and set it on a baseline, the cap height is the distance between the baseline and the top of the capitalized letters. Letters with ascenders, such as a lowercase b, will have a height that extends above the cap height, while letters with descenders, like a lowercase y, will descend below the baseline. The X height is literally the height of the letter X. This is important because fonts that have tall X heights are more legible at small font sizes because of the amount of white space around the letter forms. When using CSS, an M is a scalable unit of size that is relative to the font size of its parent element. So if you set the font size to 16 pixels, then 2M is 2 times the font size, or 32 pixels. M's can also be used for other properties other than those related to typography. So you could set a padding of 2 M's, which would also be 32 pixels. Because the size became dependent on the parent element, another system was developed called Rem, or root M. A Rem is also a scalable unit of size, but it is only relative to the root font size set for the HTML document. In this case, we set the root font size for the document and determine size as relative to the root M. To understand the difference, here we have HTML code. We have a section with an ID of section 1, and within that section, we have a H3 heading element that says this section header is 40 pixels, and a P element that says this paragraph text is 16 pixels. Now, on the next slide, we have CSS. HTML body, we have set the font size to 16 pixels. Section, font size is 20 pixels. H3, font size to M. P, font size 1 rem. We use 16 pixels as the root HTML font size to reflect the standard size we determine from the points to pixels conversion. However, we can set this to whatever we want. The size of the P text will be 16 pixels, or 1 times the root element font size of 16 pixels, the font size of the HTML document. The size of the H3 text will be 40 pixels, or 2 times the font size of the parent element, which is section that has a font size of 20 pixels. Points and picas are examples of absolute sizes, while M's and Rems are examples of relative sizes. Absolute sizes are better for accuracy. However, we have been moving to relative sizes because of responsive design. We want our type to be scalable to different size screens on which our websites will display. Another method for developing a scalable design is to use percentages. When using percentages for our typography, 100% is equal to the current font size of the parent element. From our points to pixels presentation, the default font size for our browser is 16 pixels. So 100% is equal to 16 pixels. Since that would represent our body type, we may have headings that are 150% or 24 pixels, or 200% or 32 pixels. Let's look at an example. In our HTML, we have a section with an ID of section 2. It has both an H3 and H4 heading and paragraph text. The H3 heading is 200%, the paragraph text is 100%, and the subhead, or H4 heading, is 150%. In our CSS, the HTML and body are set to a font size of 16 pixels. An H3 heading is set to 200%, an H4 heading is set to 150%, and paragraph text is set to a font size of 100%. If we don't specify the font size of the section, it will inherit the font size of 16 pixels from the body element. This shows how this would look. But since percentages act like M's in that they cascade or are relative to the parent element, if we change the section font size to a new value, this affects our results. So let's look at an example. In section 3, we now have an H3 heading that will now be 64 pixels, or 200% of the section font size. The paragraph text will be 32 pixels, or 100% of the section font size. And the H4 heading, subhead, will be 48 pixels, or 150% of the section font size. These changes occur because the section font size is 2 times the HTML or body font size that is set to the default of 16 pixels. If we look at our CSS, we have added a CSS rule for section where the font size is 200%. By increasing the section font size to 200%, we now have a different result for our paragraph and headings. The paragraph text is now 32 pixels, the section font size is now 32 pixels, and the paragraph text is 100% of that. Similarly, the H3 heading is 64 pixels, which is 200% of the 32 pixels, and the H4 heading is 48 pixels, or 150% of the 32 pixels. Percentages are often used for our container sizes in a responsive layout, since screens can be our mobile phone, a 13 to 15-inch laptop, to desktops that may be 21 inches or larger. We may or may not want our content to span the width of the screen. So for laptop or desktop, we may want to limit our content to a width of 60 to 80%, while on mobile we may want it to go to 80 to 100%. And while elements may sit comfortably side by side on a laptop or desktop, on a mobile, these elements may need to stack vertically instead. In this example, we have limited our container with our content to 80% the full width of the browser. In the laptop example, we have elements that are approximately half the container width sitting side by side, and in a second example, approximately 70% to 30%. When the same information is presented on a smaller screen, such as mobile, our responsive layout allows each element to go full width, and they stack vertically instead. Presented by Designers Learn Code.